Students, today we have a new technique for you. Mr. Hevel, we're going to teach the students how to come up with a delta H other than using the heat of formation table.
Indeed, yes. This is known as Hess's law. Okay, so there's different ways to calculate delta H. Hess's law is one method. Okay, and it really depends on what information you're given as to what technique to use.
Mm-hmm.
So to use Hess's law, you're going to be given some thermochemical equations. Now that's a balanced chemical reaction, and it gives you the enthalpy change for that reaction. If I see this sort of thing, right away I'm thinking, oh, this is probably Hess's law.
Mm-hmm.
Okay? Now, the rules to play the game with Hess's law are very simple. Okay? We can manipulate these equations in several ways. So, if I decide to multiply an equation through by some number, 2, 3, 10, whatever, all the coefficients would be multiplied, and you'd have to remember to multiply delta H by the same term.
Mm-hmm.
For instance, if you use 2 moles of acetylene, C2H2, and everything's doubled, you're going to release twice the energy. Okay, that's one thing to keep in mind. Second thing is that if you flip an equation over, n for n, then you change the sign on delta H. If it is negative now, it'll become positive. And then the final idea is that we can add equations together, and we can cancel items out that are identical on opposite sides of the arrow.
Like when we added half reactions together.
Like when we added half reactions. Yep, good example of that. So here's our goal. Find the change in enthalpy for the decomposition of acetylene into its elements. And then they're going to give us these thermochemical equations. All right. So the first thing we'd have to decide is, well, what exactly is this decomposition reaction look like?
Mm-hmm.
Do you have that pictured in your head? Okay, because I'm going to have C2H2. Now you have to be careful with phases here too. Okay, because the enthalpy change is based on the phase. This is a gas. Okay, and we're going to decompose it into its elements. Okay, this is why they don't let just anybody into Chem AP. What elements are required to make acetylene?
Oh, Mr. Hevel, you're
Carbon.
good.
I'm telling you, this thins out a lot of people right here. Right, it takes carbon and hydrogen to make acetylene. Those are the elements. Now, of course, hydrogen is diatomic, right? So don't forget about that. And in its natural state, it's a gas. And carbon is a solid. So it's going to be solid carbon. And let's see, I guess I better balance it, Mr. Moore?
Yeah, let's balance it.
Yeah, okay. Put a 2 there. So this is the equation we're trying to create.
Mm-hmm.
I want to know the change in enthalpy for this. We're going to manipulate these equations to create this one. So here we go. Notice that I have C2H2 on the left, which is where I want it. It even has a 1 in front of it, like I want it in the final form. C2H2 doesn't show up anywhere else in the problem. So this equation has to remain the way it's written,
Mm-hmm.
because it'll put C2H2 exactly where I want it. Okay, now what do you think's better? Should I rewrite it over here? You think that's easier?
Yeah, I think we're going to want to rewrite them
Okay.
anyway. Yep, go ahead.
Yeah, let me take a minute and just do that. So this top equation is going to remain unaltered, right? Acetylene plus 5/2 oxygen. Right, this is really the combustion of acetylene, right? 2 CO2. Am I going to run out of room? Probably. H2O. And delta H.
Yeah, squeeze the delta H in there.
I'm going to squeeze it in right here. It's negative, whatever. 1299.5. Probably going to go behind the smart board, aren't I?
No, you're fine. Go ahead, just
Is it
keep
okay?
writing. Yep.
I don't know if I can keep writing.
You're strong, Mr. Hell. Just push that smart
I'd
word
love
out
to
your
be.
way.
Okay, so there's my first reactant, or my first item, I'll say maybe, placed exactly where I want it.
Yeah, so what about all that other stuff?
Well, what we're hoping is that if I get the items I want in my final equation in the right position with the right coefficient, all the other stuff's gonna cancel out.
Oh, I love it when that happens.
Yeah, it's a fabulous thing. And actually, if it doesn't cancel out, there's only one of two possibilities. Either you made a mistake or the person writing the problem made a mistake.
Mm-hmm.
Yeah. Yeah, everything else with the clutter, we'll say, should cancel out for us.
Okay.
All right, what else should we go for here? Let's see, now, one of my little tips is that, well, let's see, I don't want to say that, I'm looking at where I'm trying to head. Okay, let's look for carbon.
Mm-hmm.
I need carbon on the right, and I need a 2 in front of it.
Mm-hmm.
So I'm hunting through here, looking to see if I can find that. And this is the only place I see carbon, but I need a 2 here. So guess what? We're going to have to double this equation. So let's do that over on the other side here. So I'll have 2 CO2 plus, oops, not plus, yields, 2 carbon plus 2 O2s. And remember now that we have to double delta H.
Mm-hmm.
Okay, so that's going to be, brain fade, double 393.5. I'm just going to do this.
That'll work. Yep.
I like to do that anyways because then point out that, hey, we doubled the number.
Mm-hmm.
All right, home stretch. We need hydrogen on the right with a 1 in front of it. And lo and behold, over here I find hydrogen with a 1 in front of it, but it's on the wrong side of the equation. So,
Yeah.
so take a guess what we'll have to do. We're going to have to flip this equation end for end. And when we do that, we're going to have to change the sign on our delta H value. So let's flip it over. Okay, so liquid water, H2, and half an oxygen. And delta H now is the opposite of negative 285.5. Hopefully you can read my writing.
It's fine.
All right, so now, moment of truth. Let's see what happens here. So I have my C2H2. All right, I got that thing where I want it. Now, can we cancel stuff out? Let's see. Well, look at this. I've got 2 CO2s on the left. I've got 2 CO2s on the right.
Mm-hmm.
So I can drop that out. I know I don't want oxygen in my final equation. I'm hoping that cancels out. So I've got 2.5 O2s here. And on the left, on the right over here, I have 2 and then a half. So the oxygen's all going to cancel. 2.5 on each side. That's a good deal. Now, what about the water? I don't want any water in my final equation. And look at that, I have water on the left and on the right. So that's going to cancel. And what I have left, I think, is what I want. Put a plus there, but I didn't mean it. Okay, so now I'm going to have my H2. And my 2 carbons. So I'm satisfied that I matched my balanced equation. I've gotten the 3 items that I want there.
Mm-hmm.
And now I just have to do the math, right? Negative 1299.5. Figure that out.
So we added these three chemical equations together, and when you do that, you can add the delta H's together, and the total delta H that you get would be the delta H for this target equation.
All right, so now I took my other calculator. So anyways, 93 times 2. Yep, 787, that makes sense. So I'm going to have negative 787 plus negative 1299.5. And then plus, now this is going to be a positive, right?
Yep.
We have to remember we're taking the opposite of
Be
that.
careful with those signs.
Yep, that's easy thing to mess up. 285.5. So I got negative 1,801 kilojoules. Okay, there's Hess's law. That's one way to theoretically calculate delta H.
Looks pretty easy, Mr. Hubble. It's not bad.
Yeah, I
Just
mean,
take
it
some
can only
equations
get
and manipulate
harder,
them.
right, if they give you more equations to use.
Mm-hmm.
And the ultimate in cruelty is to give an extra equation.
Yes.
That's not very nice to me.
Think the Zoom dolls might do that to them?
No, Mr. Moore would though.
Sounds
I
good.
had to say.
So is there another way to find delta H for a reaction?
Oh, well, I believe there is, Mr. Moore. Actually, you're very intuitive with that. And that would be bond energy. Okay, so there's basically three ways to calculate delta H using data you're looking up. You can use enthalpy of formations,
Mm-hmm.
you can use Hess's law, or you can use bond energy. Okay? Now, to do bond energy, obviously, you're going to have a table of bond energies available. This is the energy required to either break or form a chemical bond. Okay?
So it takes the same amount of energy to both break and form a bond.
True, but the sign changes,
Okay.
right? So when you form bonds, energy is released. Exothermic will make it a negative. When bonds form, energy comes in.
No, yeah, it was.
I said, did I say it right the first time?
Yeah. When bonds form, energy is
It's
given off.
exothermic.
Yeah.
When bonds break, it's
Mhm.
endothermic, and we'll have to make the energy positive.
Mhm.
Sorry about that.
Okay, so that looks familiar, this equation. We
Yeah.
just kept the first equation from what was given in the Hess's law example,
Right.
the combustion of acetylene.
Yes.
C2H2 plus 5 half O2 makes CO2 in water.
Now, the one thing that's tricky about bond energy is you have to know the structure of the molecules, which may or may not be obvious to you.
Mm-hmm.
So one disadvantage for you at the moment is we didn't do organic chemistry early in the year, so you don't know the structure of some of these.
Right.
For those of you who haven't been self-studying organic, which will be very few of you, but if you haven't been self-studying organic, C2H2 looks like this. Okay, there's a triple bond between the two carbon atoms. Okay, I don't know, do you know the structure of oxygen? Is there a single, double, or triple bond in an O2 molecule?
Have to go back to our Chem 1 knowledge.
Yeah, you have to know that to be able to do bond energy. So oxygen has a double bond.
Mm-hmm.
Okay, well, same thing for CO2. What's the structure look like? Okay, there's two double bonds in the CO2 molecule. And water, I'm pretty confident you would know. Right, now, I'm not really bothering to put in all the unshared electrons. For you purists out there,
Does look naked without them.
it does a little bit, Okay, but we're focusing on the bonds.
Yep.
Okay, so in order to do this, right, we're going to have to break reactant bonds. That means energy is going to go in, and we're going to have to form product bonds, and that means energy is going to go out. It's going to be exothermic and negative.
So in the reactants, all those atoms that are currently bonded to each other have to come apart.
Right.
And that's endothermic. Energy must be put in to break the bonds.
Right. Right. Sometimes you get lucky. Sometimes you don't have to break all the reactant bonds because some of them remain in the products.
Mm-hmm.
And then you don't have to worry about breaking and reforming the same bond. But I don't think that's going to happen here.
Yeah, it doesn't look like it.
It doesn't look like it, okay? Now also, when you're doing bond energy and you say, oh, I want to find delta H, okay, it's bonds broken minus bonds formed. And what that really means is reactants minus products, which can be tricky because if you may remember, if you're finding delta H using enthalpy of formation, it's products minus reactants. Normally, when you find change in something, it's final minus initial. With bond energy, it's backwards. That's what I try to remember is bond energy is backwards from the way things normally work.
It's just like chemistry to always have an exception.
Always
Here's
got
our
a
exception
zinger.
for delta H.
Always
Yep.
a zinger. Okay? So you ready? Here we go. So I'm going to start over here with the reactants. It looks like we're going to have to break 2 carbon to hydrogen bonds. Now, I think what I usually do in class is I write it out just in symbols and then I plug in the numbers just to make sure people know what we're doing here.
I don't. I just tell the students to figure it out.
Figure it out. Okay, so we're going to have to break 2 C to H bonds. We're going to have to break 1 triple bond between carbons.
Ooh, that takes a lot of energy.
Yep. Okay, now we've taken care of our acetylene. We're going to have to break an oxygen double bond. Now, one other thing I just realized I didn't point out exactly is we have to factor these coefficients in.
Yep.
So there's a 1 in front of the acetylene, but notice there's a 5/2 in front of the oxygen. So I'm going to break 1 O, double bond O bond, but I also have to multiply by this coefficient that's up
Mhm.
here. Okay, there's our reactants, bonds broken. Put it in a big bracket here. Minus. Okay, now let's tackle our product side. So we're going to have to form 2 carbon to carbon double bonds, carbon to oxygen
Oxygen.
double bonds, sorry. But remember there's a 2 up here. So really we're going to have 4 carbon to oxygen double bonds. And then we'll have to make 2 oxygen to hydrogen bonds. And there's only a 1 coefficient up here, so that's my total count. Okay, so now I've identified the bonds I'm going to break and then form. It's time to go to the bond energy table and look up values. Okay, so there's a table in the Zumdahl book in chapter 8.
Yep. Now this is in chapter 8. This is the chapter on bonding.
Yeah.
Look at what the title of the table says.
Can you read it
It's
again?
perfect. No, we can read it fine. Average bond energies in kilojoules per mole. So like the first thing there is the hydrogen single bonded to the hydrogen, 432. So that means it takes 432 kilojoules to break a mole of hydrogen-hydrogen single bonds. So what do we have up here? We have
We got a carbon
two
to hydrogen.
carbon to hydrogens. So you see that number right there in the middle of the screen?
I wanna say it's
413.
413.
413.
Okay.
Should we have the students memorize this table, Mr. Help, for quick recall?
That's
Time is of the essence, right?
It absolutely is.
Yeah. Here you go. Maybe I'll just leave that on there for a few seconds. Got it memorized? Okay.
Yeah.
So a carbon-carbon triple bond is
Yep,
next.
that's next.
I'll just leave the camera on this so I don't keep flipping up.
Yeah.
839. See it over on the right, second from the top. 839.
39, got it.
5 halves O to O double bond. 495. Right under the carbon-carbon triple bond. So those are all our breaking bonds, and then we'll form some bonds too. 4
Yep.
C to O double bonds.
Yep.
So C to O double bond is 745. Well, you know what, Mr.
What?
Helvel, there
Yeah.
is a little footnote
Be
there
careful.
in the book.
Yeah.
See this one down here? If it's carbon dioxide, the bond energy is 799. So this tells you how much energy it takes to break that bond and how much energy is given off when the bond forms. So Mr. Helvel is now making those values, well, I guess they're negative. He's got the negative sign out in front, but we're subtracting that all the.
Right. I do it, I
Yeah.
do it as one quantity,
Mhm.
without however you want to do it.
So then the HO single bond is our last one. We need 2 of those. And HO is right there in the middle of the screen, 467.
Okay, awesome. We've got our numbers plugged in.
So yeah, now we just calculate that out. We break all those bonds at the beginning, form all those bonds at the end. That much energy is taken in to break the bonds, that much energy is given off when the bonds form. And the overall delta H.
Okay, so if I haven't goofed up here, our bonds broken is 2,902.5 kilojoules minus okay, so bonds broken minus bonds formed. So drum roll finally. What's delta H? 2905, oops, yeah, 2902.5 minus 4130. I get negative 1227.5 kilojoules.
So if you remember from the Hess's law example, the delta H of that first reaction was negative 1299. Now doing it with a different technique using bond energies, it's close, but it's not the same. Mr. Helvel, what do we trust more, the heat of formation table values or the bond energy
Yeah, bond
values?
energy, right? Yeah, so first off, I would say, like Mr. Moore says, it doesn't bother me these don't match. They're close, but they don't match because it's 2 different data sources.
Mhm.
But also, bond energies are approximate. Bond energies vary depending on the molecule.
Mhm.
So this bond energy number is much more of an approximation. When you're using Hess's law or enthalpy of formation, those values are going to be much more accurate.
So 2 different ways to find delta H.
Yeah, there
Well,
you go.
that we've seen today, and then
That we've
the
seen today.
products minus reactants for the heat of formation.
Right.
Yep. And look at that. How many other words in the English language do you have 3 S's in a row? 3 of any letter
That's
in
right.
a row. It's fabulous.
It is fabulous.